really interested, you will attend in the class. You should be present. If you have any doubt at any point, which portion I am discussing, you can ask. Even if in every batch I am taking some extra classes, I will take some extra classes. I have no objection. If you want, then you can record by your own mobile. There is no problem. Recording is allowed. There is no problem. I am not saying that you cannot record. You are present in your home. If you want, you can record by your own mobile. There is no problem. That means those who are present, they can record. Those who are not present, if I will record, it will be there. Then whenever they want, they will see those things. So my intention is that all of you should be present in the class. Whether it is online or offline, you should be present. If you will be present, then you don't require recording. Even if you are present in the class and you want recording, then you can do by your own, by yourself. There is no problem. Okay, so this is the harmonic motion or periodic motion. If in the periodic motion the body oscillates back and forth, then we are saying it is oscillatory or vibratory motion. For example, the balance wheel of a watch, the bob of a pendulum clock, the prongs of a tuning fork, etc. This is about harmonic motion, because I will not go in detail these things. If you want, you can go through the books, you will get those things. Now, regarding this simple harmonic motion, I think all of you have read many things about simple harmonic motion. Anybody who can say that what is simple harmonic motion? I can say that a simple harmonic motion, you see, first a harmonic motion, then I have written simple harmonic. So, from its name, it is clear that a simple harmonic motion is the simplest example of a harmonic motion, in which the oscillator covers equal path. If you will say that OA equal to OB, it will say that OA equal to OB, OA equal to OB. If the body covers equal path on either side of the equilibrium position, then it is said to be simple harmonic motion. It is one kind of definition. The simplest example, it is a simplest example of a harmonic motion in which the oscillator covers the equal path OA and OB on either side of the equilibrium position. If AO is not equal to OB, then the oscillator has a harmonic motion, but not simple harmonic motion. The equilibrium position of O is defined as the position where the net force acting on the oscillator is zero. Such a position is called mean position. This is one kind of definition of a simple harmonic motion. Then another kind of a definition, I think all of you know, in terms of a restoring force. I am not going in detail. I am writing that you know that if you displace any harmonic oscillator, then by applying some force, then there exists some restoring force which tries to return its original position. That restoring force is directly proportional to, I think all of you know, the restoring force is directly proportional to the displacement and it opposes the increase in it. So we can write F is directly proportional to X, and we can write F equal to minus of X. Since it opposes, negative sign is given. So this minus sign, what is the physical significance of this negative sign? This minus sign, K is a positive constant, but this minus sign indicates that F opposes increase in X. F opposes increase in X. Already we have said that restoring force is directly proportional to displacement and opposes its increase. Its increase means that the displacement is increase. We know that mathematics is the language of physics. So here, the negative sign, what is the physical significance of this negative sign? The negative sign indicates that if it opposes the increase in x. And this positive constant k is known as force constant of motion, force constant of motion, or spring constant, or stiffness. I think all of you know this k is known as force constant. Force constant of motion, or we can say that spring constant, or stiffness. I think all of you know these names. In some books it is written force constant of motion, in some books it is written spring constant, and in somewhere also it is written stiffness. This is known as Hooke's law. This F equal to minus kx is known as Hooke's law. This is known as Hooke's law. This is the statement of Hooke's law for elastic forces. So from this we can give the definition of a simple harmonic motion. It's like that. Simple harmonic motion is the motion in which the restoring force is proportional to the displacement, in which the restoring force is proportional to the displacement from the mean position and opposes its increase. Clear? So this is the second kind of definition of SHL. Then also we have to derive the equation of motion. Equation of motion for SHL. What is that? From Newton's second law, we know that F equal to mg square x by dt square. F equal to ma. And A equal to d square x by dt square. So we can write again, from that Hooke's law, we know that F equal to minus kx. So combining these two equations, we can write that d square x by dt square plus k by mx equal to 0. This k by m is omega square. And this equation, that equation number 3, is the equation of SHL. This is the equation of SHL. I think all of you know this is the equation of SHL. So from this we can write another kind of definition of SHL is that where the acceleration of the body is proportional and opposite in sign to the displacement. Where the body, acceleration of the body in SHM is proportional, within bracket you may write, and opposite in sign to the displacement. So these are different kinds of definition of SHM. Number 1, simplest one. Number 2, regarding that restoring force. Number 3, containing acceleration. So these are 3 different kinds of definition of SHM. We can use any one in the examination if it is asked. Now you see this equation. What kind of equation it is? The equation of motion of a SHM is a homogeneous second order ordinary differential equation with constant coefficients. Again I am repeating. The equation of motion of a SHM is a homogeneous, if you want you may note down, is a homogeneous second order ordinary differential equation with constant coefficients. I think in mathematics you are also reading different kinds of differential equations. It is a homogeneous second order ordinary differential equation with constant coefficients. In mathematics you have read, otherwise in mathematics also you will read what is the meaning of a homogeneous second order ordinary differential equation with constant coefficients. In your 11th or 12th class also you have read those things. Now, what will be the solution of this equation? I think in your 11th or 12th class you have derived the solution. If not, then you can go through the book because it is not present, detailed derivation is not given in the syllabus. So, the solution of this, we can write its the solution in a trigonometric function, its the solution in exponential function, its the solution can be written in power series solution. For details, you can go through the books. For trigonometric solution, we can write xt equal to a sin omega t. You can write a sin omega t. You can also substitute here, then we will see that it's k by m is omega square. Or you may write xt as d cos omega t. Either sine function or cosine function. In general, we can write the solution of this equation of motion for SHM at xt equal to a sin omega t plus b cos omega t. This is the general solution of equation of motion for SHM. This is the trigonometric solution. Similarly, also, if you want to cross check, then you can also cross check. Take xt, x, find dx by dt, then d square x by dt square, and check whether it is correct or not. That means when we are saying this is the solution, if this equation, if equation number 4 satisfied equation number 3, then we can say that equation number 4 is a solution of equation number 3. Clear? Similarly, it's a solution in exponential form. It's an exponential solution. Can be written as xt as c1 e to the power I cos omega t. Or its solution can also be written as xt as c2 or c2 e to the power minus I omega t. Similarly, in general, also we can write the solution as xt equal to c1 e to the power I omega t plus c2 e to the power minus I omega t. This is the general solution of this equation. Equation number 5 is the general solution of equation number 3 in exponential form. Similarly, its solution is also available in power series. Since the solution of equation number 3, that is the differential equation for SHM, can be expressed either in trigonometric form or in exponential form or in power series form. That is why it is said to be a simple harmonic motion. Since its solution can be obtained
बनाना चाहिए था। ये स्लाइड्स तो तुम्हें बाद में नहीं मिलेगा ना? क्वेश्चन भी इसमें से ही आएगा, तो इससे इम्पोर्टेंट और क्या ही हो सकता है। ये वाला सॉल्यूशन पढ़े थे क्या?
Solution can be expressed in any form, in things that either trigonometric or exponential or power series. That is why we are saying that this is simple harmonic motion is very simple. And other terms like velocity and acceleration of SHM, then total energy, kinetic energy, potential energy, total energy, you know those things. So these things you can read from your either your 11th or 12th class note or any book that is written as your waves and oscillation, any book available with you. Since you are now in there is no lockdown, you can go to the market, you can purchase any book available with you. This textbook of oscillations and waves, any book, then you will go in detail about this SCP. Now, this is what we are considering a single SHM. Now, in our day-to-day life, we are coming across the phenomena or situations where simultaneously two or more SHMs or harmonic motions are implemented. For example, the diaphragm of microphone or human eardrum is subjected simultaneously to various vibrations. So, in order to obtain the resultant of two or more harmonic oscillations, in order to obtain the resultant of two or more harmonic oscillations, we are using a very important principle which is known as superposition principle. Which is known as superposition principle. Which is known as superposition principle. If you want, you can write down the statement. This principle states that I will upload the study materials for this class. Not this SHM, these things, what is present in your syllabus. Basic things you will read from the book. The resultant of two or more harmonic displacements. The resultant of two or more harmonic displacements.
So the
resultant of two or more harmonic displacements is simply the algebraic sum of individual displacements. Is simply the algebraic sum of the individual displacements. After taking 2-3 classes, I will upload the study materials for this unit. The resultant of two or more harmonic displacements is simply the algebraic sum of individual displacements. For example, if you will consider x1 and x2, if you will consider x1 and x2, are two individual displacements caused by two different SHMs, then the resultant displacement will be x, which is equal to x1 plus x2. Actually, this principle was first stated by Thomas Young. In 1802. While he was studying the interference phenomenon of light waves, he was first stated this principle. I think interference is started in your class. So for this one, we are using the superposition principle. Now the superposition can be obtained. So by superposition of waves, one can explain the interference, diffraction, polarization, Brownian motion, diffusion, viscosity, etc. And this superposition can be obtained by following methods. The superposition can be obtained by the following methods. There are different methods. Number one, put down analytical method. Number two, that is graphical method. And number three, method using complex quantities. Method using complex quantities. So these are the different methods by which we can obtain the superposition of two or more harmonic oscillations. Okay, now we will discuss about this superposition principle. What is that superposition principle? Already statement, I have called that statement. The resultant of two or more harmonic displacements is simply the algebraic sum of individual displacements. Or this superposition principle can be written like this. The superposition principle can be applied only when the equation of motion is linear. Only when the equation of motion is linear. It does not apply if the equations are non-linear. We cannot apply the superposition principle if the equations are non-linear. Clear? So superposition, again I am saying the statement, superposition principle can be applied only to linear differential equations. Superposition principle can be applied only to linear differential equations. Now we will prove this one. In the examination it may be asked, state and prove superposition principle. So superposition principle can be applied, or superposition principle holds only for linear differential equations. Okay. Now, in order to prove any statement, there are different methods, you know. Number one, direct method. If it is given A equal to B, prove this one. Then what you are doing? You have started from A and reached at B. That is the direct method. In another method, I think mathematical induction method. All of you have solved more than, I can say that 100 problems using this induction method in your 11th or 12th class. Another method is there is another method which is known as contrapositive method. What is that one? If it is given proof A equal to B, then you will start from negation B and reach that negation A. If you will start from negation B and reach that negation A, then that is equivalent to your A equal to B. Okay, this is known as contrapositive method, and using that method, we will try to prove this superposition principle. What is that superposition principle? This is superposition principle can be applied only to linear differential equations. Superposition principle, linear differential equations. A, B. We will start from negation B. That means we will take non-linear differential equations. Then we will prove that superposition principle cannot be applied. Clear to this point? All of you try to understand what is the technique we are using for proving the superposition principle. Statement is superposition principle can be applied to linear differential equations. I will start from negation B. That means I will take a non-linear differential equation. Then we will prove we cannot apply superposition principle. Or, again I am repeating, we will take a non-linear differential equation. We will apply the superposition principle. Then we will reach at the contradiction. That means we cannot apply the superposition principle to non-linear differential equations. Everybody clear what is the technique? We will consider a non-linear differential equation. Then we will apply superposition principle. We will reach at the contradiction. Then we will say that it cannot be applied to the non-linear differential equations. Everybody clear? So in order to prove this one, let us consider a non-linear differential equations. We know that d square x by dt square equal to minus omega square x is the linear differential equation. Already we know that linear differential equation of a system. So if we add some extra terms having x to the power 2, x to the power 3, etc., then we will say that it is a non-linear differential equation. So let us consider this non-linear differential equation because it contains the terms like x square, x3, etc. And it is not easy to solve these non-linear differential equations. So now let us assume x1. This x is the function of a t. Let us consider x1t and x2t are two solutions of equation number 1. Are two solutions of equation number 1. If x1 is the solution of equation number 1, then what will be? If x1 and x2 are the solutions of equation number 1, then they should satisfy that one, that equation number 1. So we can write d square x1 by dt square plus is equal to minus omega square x1 alpha x1 square beta x1 cube plus dot. This is equation number 2. Similarly, d square x2 by dt square minus omega square x2 plus alpha x2 square beta x2 cube, like this. Everybody clear? What we have done? We have taken a non-linear differential equation. Then we have assumed these are the two solutions of this equation. That means if they are the solutions of equation number 1, they should satisfy equation number 1. As a result, we got equation number 2 and 3. Clear? Now, if we consider x, which is equal to the sum of x1 and x2. Let us assume that x, which is equal to x1 plus x2, is a solution of equation number 1. That means we are applying the superposition principle here. Here means to the non-linear differential equations. So if x equal to x1 plus x2 is a solution of equation number 1, then what will be? I can write here d square x by dt square. X means I can write here x1 plus x2. This will be minus omega square x1 plus x2 plus alpha x square means x1 plus x2 square plus beta x square, sorry, x cube, x1 plus x2 cube, like this. So we can write like this. Everybody clear? Now, if you add equation number 2 and 3, if we add equation number 2 and 3, then what will we get? D square x1 by dt square plus d square x2 by dt square equal to minus omega square x1 minus omega square x2 plus alpha x1 square alpha x2 square plus beta x1 cube plus beta x2 cube plus dot dot dot. Okay. Now you will see, now if you compare equation number 4 and 5. Now these two equations are agree. These two equations agree if and only if. We can say LHS equal to, LHS of both are equal, then RHS of both are equal. So we can write d square x1 plus x2 by dt square equal to d square x1 plus d square x2 by dt by dt. Similarly, minus omega square x1 plus x2 equal to minus omega square x1 minus omega square x2 and alpha x1 plus x2 square equal to alpha x1 square alpha x2 square, or we can say that alpha x1 square plus x2 square. Similarly, beta x1 plus x2 cube equal to beta x1 cube beta x2 cube, that is beta x1 plus. So we can say that 6, 7, 8, 9. So if we have applied x equal to x1 plus x2 as the solution of equation number 1, then we have obtained equation. Then we have obtained that equation number 6, 7, 8, and 9. So these equations agree if and only if the following conditions, equation number 6, 7, 8, 9 are satisfied. But you will see that equation number 6 and 7 are true. 6 and 7 are true, whereas equation number 8 and 9 are not true. Unless and until alpha equal to 0 and beta equal to 0. If alpha equal to 0 and beta equal to 0, then this equation number 8 exists, 8 and 9 will be true. So we can say that actually your x1 plus x2 square equal to x1 square plus x2 square. Similarly, x1 plus x2 whole cube equal to x1 cube plus x2 cube, which are not true. Why we have reached at this contradiction? Because we have applied the superposition principle to a non-linear differential equation. That is why we have reached at these contradiction points. Clear to this?
Sir, no, sir, one doubt is there.
That is why we cannot apply the superposition principle to a non-linear differential equation. Or in other words, we can say that superposition principle can be applied to linear differentials only.
Sir,
any doubt? Anybody has any doubt at any point?
Yes, sir, one doubt.
Yes?
Sir, according to linear differential equation, it is that the right-hand side of the equation should be a function of x. So, sir, it was the function of it. It was minus omega square x plus alpha x plus beta x square. So it is a function of x. So sir, how it is non-linear then?
Non-linear means since x square only, linear means power should be 1. Linear means power should be 1. Since here x square, that is why I said since x square, x cube, etc. terms are present, that is why it is not a linear equation. It is a non-linear differential equation. A linear differential equation is the one that contains the terms that depends only on the first power of the variable and its derivatives. This is the definition of a linear differential equation. I think you have forgotten the definition of a linear differential equation. Only that.
No, sir, but sir, then like it should be the function of x. Sir didn't mention that power should be 1 for the function of x to be linear.
No, for linear equation, always power should be 1. Since we have taken alpha x square plus beta x cube, that is why it is a non-linear differential equation. Not only that a function of x, that is perhaps from where you have read or what you have remembered, that is not correct. For linear differential equation, so a linear differential equation is the one or it is the equation which contains the terms that depends only on the first power of the variable and its derivative. This is the definition of a linear differential equation. Since in the equation number 1, which I have raised, we have written it is that d square x by dt square equal to minus omega square x plus alpha x1 square, alpha x square plus beta x cube. That is why it is a non-linear differential equation. Clear?
फिजिक्स का तुम बताओगे?
Any other doubt? What we have
Physics
done,
का
again I
notes
am
तुम
repeating.
बनाओगे?
Now, we have taken a non-linear differential equation. Then we have applied the superposition principle. As a result, we have reached at the contradiction point. That means we cannot apply the superposition principle to a non-linear differential equation. In other words, we can say that superposition principle can be applied only to linear differential equations. Everybody clear? This is the statement as well as its proof. Very important principle, which will be used frequently in your waves oscillation as well as interference, diffraction, etc. So after this, now we will consider the superposition of a two
समझा दूंगा.
harmonic oscillations. In your syllabus, you will see that the superposition of two perpendicular harmonic oscillations is given.
Organic chemistry.
Very briefly, I am
Organic
saying
chemistry.
superposition of two harmonic oscillations. Superposition of two harmonic oscillations. Harmonic oscillations. These harmonic oscillations may be linear or may be perpendicular. Very briefly, I am saying. So, what will be the resultant motion due to superposition of two harmonic oscillations? Linear harmonic motions. What will be the resultant motion due to superposition of two perpendicular harmonic oscillations? Again, under these linear motions, we will consider two harmonic oscillations having equal frequency or same frequency, having different frequencies. And here also two perpendicular harmonic oscillations having same frequency, having different frequencies. So, what will be the resultant motion due to superposition of two linear means we can say that two collinear harmonic oscillations. Linear means better you may write to collinear harmonic oscillations. So the resultant motion due to superposition of two collinear harmonic oscillations is a harmonic motion. I think if you have done the calculations like you have taken x in your 10 plus 2 class, I think you have taken x equal. Now, what will be the resultant motion due to superposition of two collinear harmonic oscillations having different frequencies? The resultant is beats. You have lived beat phenomena very well and solved the problems more than 100 problems regarding the bits. This portion is not present in your syllabus since you have already read in your 10 plus 2 classes. The remaining part, that what will be the resultant motion due to superposition of two perpendicular harmonic oscillations having same frequency? What will be the resultant motion due to two perpendicular harmonic oscillations having different frequency? That we will discuss in detail in the next class. This portion is present in your syllabus. Since this part you have read in your 10 plus 2 classes, either 11th or 12th classes, all of you go through your previous notes. Otherwise, you can go through any waves oscillation book available with you in the nearby market. You can purchase one, you read very well, thoroughly, then some problems will be asked. You will be able to answer those questions. So these details you can go through the book. If you have doubt, then you can ask. In our book, we have done in detail. You may follow that one or any waves oscillation book you can follow. There is no fast and hard rule. Which one I am following, you will follow. That is not my principle. In any book you can read, waves oscillation book. Then this part we will discuss detail in the next class. If any doubt, you can ask. So if you are those who have doubts, my suggestion is you should join before at least 5 minutes before in the class. Then you can ask your doubts. Because I am joining more than 10 minutes before. So if anybody has any doubt what I am discussing in the class, you can ask the doubts. Whether I will be able to answer or not, that depends upon my knowledge. If possible by me, then I will give the answer. Otherwise, I will try, or finally I say that I am not able to answer your question. This will not create any problem. Nobody in the universe, not only that your SAHOO sir or Mandal sir, will be able to answer all the questions. Nobody in the universe, in our universe, can say that I can give the answer of all the questions or the doubts. The universe research is going on to solve the problems, to solve the unproblems, to solve the unsolved problems. That is why the research is going on to solve the problems. So nobody can say that I can give the answer of all the questions, or physics or whatever may be the subject. If anybody will say that I can give the answer of all the questions or all the problems, then he or she will be able to stop the research going on in the entire universe. Okay? So you can give your attendance. Respond your roll call. Roll number 1, Orin Saha. I will take the attendance accordingly. You can give your response. Roll number 1, Orin Saha. Roll number 2, Horace Kumar. Roll number 3, Priyanshu.
Present, sir.
Roll number 4, Sumit.
Present, sir.
5, Soumik.
Present, sir.
6, Purushottam.
Present, sir.
Roll number 7, Soumik Biswas. Roll number 8, Sudipta.
Yes, sir.
Roll number 9, Abhinav. Roll number 10, Yas. Roll number 11, Kesav. Roll number 12, Panishka.
Present, sir.
12,
Present, sir. Roll number 12.
13. Roll number 13. Aditya. Roll number 14.
Roll number 14 present, sir.
15.
Present, sir.
16.
Present, sir.
17.
Present, sir.
18. Puspita. 19.
19 present, sir.
20. Akash.
Present,
21.
present, sir. Akash.
21.
Present,
22.
sir.
22.
Present, sir.
23. 24.
24
25.
present, sir. 25 present, sir. 25 present.
26 present, sir.
27.
27 present, sir.
28. 29. 30.
Present, sir.
31.
Present, sir.
32.
Present, sir.
33.
Roll number 33 present, sir.
34. 35.
Present, sir.
36.
Present, sir.
37.
Present,
38.
sir.
38.
38 present, sir.
39.
The 37 present.
39.
Present, sir.
You have doubt, you may wait. 39.
Present, sir.
40.
Present, sir.
41. 42.
Present, sir. 42 present.
43. Vidisha. 44.
Present, sir.
45. 46. 47. 48. 47. 48. Gayatri.
Hello, sir.
50.
50 present, sir.
51. Rajkumar. 52. 53. 53. Anand. 54. Aditya. 55.
Present, sir. Monodeep Bauri.
56. 57. 58.
Present, sir.
59.
57 present.
Okay. 60.
Yes, sir.
61.
Present.
62. 3.
62 present, sir.
64.
Yes, sir.
65.
Present, sir.
66. 67.
66 present, sir.
68.
66 present. Present, sir.
Present, sir. 68 present.
66 present. 67 present, sir. 65 present.
70.
Present, sir. 70 present.
71.
Present, sir.
72. 73. Harsha. 74. 75.
Sir. Present.
75. 76.
Present, sir.
77.
Present, sir.
78. 9. 10. Sorry, 80.
Present, sir.
82. 83.
Present, sir.
84. Paramita. 85.
84 present, sir.
85.
85 present, sir.
86.
86 present, sir.
87. 88.
sir.
88. 89.
Present,
sir. 90. 91. 92.
Present, sir.
92. Again, I am repeating the roll
Present,
numbers.
sir.
All of you listen. Again, I am repeating
Okay.
the roll numbers which are absent in my copy. Roll number 88. Roll number 77.
Hello, sir.
78.
Hello. Roll number
77
present, sir. 77 present.
Okay. Then roll number 73. Roll number 56. Roll number 45, 46. Roll number 43.
43 present, sir.
I am calling only those who are absent in my.
The roll number
Are present.
54.
Again, wait. Roll number 29, 23,
Present, sir.
29,
Yes, sir.
23, 18, roll number 13, roll number 11, roll number 10, roll number 1, roll number 2.
Present, sir. Roll number 1 present, sir. The roll number 7 present.
I
That roll
said
number.
those-
Did you give it?
Those roll numbers I have called second time, they are absent. All others are present.
Sir, can you repeat under 10 roll number again?
Oh, okay, sir. Oh.
Roll number 2.
Sir, can you
roll
just
number
see
10,
that roll
11.
number 7 is present or not?
I am not saying those things. I am calling the roll numbers which are absent in my copy. Roll
Okay.
number 2, roll number 10, 11, 13, roll number 18, roll number 23.
Sir, roll number 18. Present.
Okay. I am calling only the second time roll numbers, those who are absent in my copy. 45, 46, 52, 56, 73. Then roll number 79, roll number 88, all others are present. Okay, thank you all. So before coming to the next class means my class, all of you should read what I have discussed. That is already you have read in your 10+2 classes. Then we will discuss about the superposition number 2 perpendicular harmonic oscillations having same frequency and having different frequency. These two cases we will discuss here in detail. Thank you all. You can leave.
Thank you, sir.